We're going to talk about angular momentum, and for the problem it goes like this. So a merry-go-round has a mass of 40 kilograms and a radius of 3 meters and can be treated as a solid disk. Now we're trying to find the magnitude and direction of the merry-go-round and the child, which is hanging right from here. Don't forget also, the problem gives you the 0.8 radians over second. Now for that, we're trying to find if it's going out of the page, or out of the board, or into the board. Now by a right hand rule, we know it spins this way, and then it's going out of the board. Now that's that. Now we're trying to find the angular momentum of the merry-go-round, which would be L rigid. Merry-go-round. Okay. And the formula is basically moment of inertia times the angular velocity. We know, since it's a solid disk, we know the formula for the moment of inertia would be 1/2 times mass times radius squared. And okay, so we know that. We substitute the values of the merry-go-round, so it's 40, which was given, the radius times 0.8, which is the angular velocity. And then you get 144 kilograms times meters squared over second. That's that. Now, since the child is on the edge, we know it's an angular momentum from a point. So, boy. Now, the formula for that would be radius times mass times velocity. Now, velocity is not given, since it's an angular velocity. An angular velocity is given, but not a tangential velocity is given. Now, for that, we substitute the value as V tangential would be W times R. So, we substitute values, which is here. This is R, this is mass of the boy, of course, which is given also, and then the angular velocity, which is given, and also the radius. Now we multiply the values and we get 216 kilograms meters squared over second. That's it.
So for part B, we want to find the conservation of angular momentum. So the boy jumps off in this direction right here, so at a 90-degree angle. So what we're going to do is add a velocity, tangential velocity of 3 meters per second. So what we do is we take our initial of our rigid object and our initial and the initial of the boy, and then we have it equal, or add them together and have it equal the final of the rigid object and the final of the boy. And normally our angular momentum for a point would be R cross mv, but we're using this equation, they equal each other, just because we have to factor in the angle. So we get 360 equals the same I as before, 1/2 mr squared times our angular velocity, and then we replace our R with the mass of the boy and then our tangential speed. Sine 90 because the boy jumps off at a 90-degree angle from the radius, and then do the math, and we get our angular velocity of the merry-go-round is 0.5 radians per second after he jumps off. In part C, the boy jumps off at a 180 degrees from the radius, so our sine here, everything's the exact same thing, except our sine is 180, which makes this whole last part equals 0. So now we can just solve this whole part, solve for our angular velocity, and our angular velocity equals 2 radians per second there. For our third part, we wanted to know, for part D, we wanted to know at what angle the boy would have to jump off to keep the angular velocity of the merry-go-round at 0.8. So now our new variable is theta over here, and we can replace, like in the past we knew our theta, we didn't know our angular velocity. Now we know our angular velocity of 0.8 and we don't know our theta. So we replace, we have our I, angular velocity that we know, times our radius, our mass of the boy, and the velocity of the boy sine theta, which we don't know theta. Do the trigonometry and the algebra there, and you get theta of 53.13. And at that point, if the boy were to jump off at that angle, the angular velocity of the merry-go-round would remain the same.